All right, today's class is about a problem called subset sum, a numerical problem. But let me just remind, it's all going to kind of fit into some of the stuff we've been doing recently. Let me just quickly remind you, because I think this part of the class is probably more new to more people than the beginning part of the class. So again, we started looking at some of these, well, really logical problems like SAT, Boolean SAT and stuff like that, just simple ands and ors. And sort of the big question was, can you get an algorithm for this? And the punchline is you can't, but not only can you not, even simpler versions of the problem like CNF-SAT, 3-SAT, we don't have algorithms for either. And moreover, one has an algorithm if and only if the other one does. So that's sort of maybe the plot twist, is not that we couldn't find an algorithm, but that we found some kind of equivalence between these problems. Okay, so that's sort of a different style of thinking. And we pushed the envelope last time by looking at the 2-SAT and max 2-SAT problem. It's like 3-SAT, but you only have 2 variables per clause. 2-SAT, you just want to satisfy the formula. Max 2-SAT, you want to satisfy as many clauses as possible. Right? So they both seem really similar to each other. They both seem really similar to 3-SAT. And we had this vote about like, oh, is it going to be hard? Is it going to be easy? And stuff like that. And even though you would think there's not much distinction between 2-SAT, max 2-SAT, and 3-SAT, it turned out for 2-SAT, there's just enough structure. We can make this implication graph that you can actually solve 2-SAT, and you can even solve it in linear time. It really reduced to, strongly connected components and a matter of reachability in that implication graph, right? So somehow 2-SAT is very special. And even though you can do 2-SAT, we didn't have an algorithm for max 2-SAT. Instead, we gave a reduction from 3-SAT to max 2-SAT, which involved sort of this complicated gadget where I took a clause with 3 variables and I produced like 10 clauses with 1 or 2 variables. We had to go through this table. It's sort of a detailed thing. But ultimately, we were able to show that first, at most 2-SAT is NP hard. At most 2-SAT is at least as hard as 3-SAT, at most 2-SAT being 1 or 2 variables per clause. And that led us to, from there it was easier to go to 2-SAT, where you have exactly 2 variables per clause. So somehow we walked away last class was, I think, an unusual or surprising conclusion that 2-SAT's easy and max 2-SAT is hard. Somehow that max allowed for just a little more degree of freedom. That's something made it so we can't do some of this 2-SAT style logic. And something very subtle is going on there. I don't have a great explanation beyond what we did last time for why max 2-SAT is so radically different than 2-SAT. Okay. No one has a great explanation. All right, so today's problem is something that you guys have probably seen a lot before, or maybe you haven't because you're so young. In the old days, there's this thing called cash, and you like go to a store and you like give them some money and you get some items, and items cost something, and then they give you back some amount of money to make up for the difference. So in America, we have quarters that are worth 25 cents, dimes that are worth 10, nickels that are worth 5, and pennies that are worth 1. I don't know how many Bitcoins are each worth. You guys could tell me. All right, so if your change was supposed to be 93 cents, they're going to give you 93 cents, and you're going to break it down into quarters, dimes, nickels, and pennies. What would you do? Like how many quarters, how many dimes, how many nickels, how many pennies? I'll start with quarters. How many quarters? All right, I'll do 3 quarters. That's 75 cents. How many dimes? All right, but 1 dime. How many nickels? And how many pennies? Okay, good. Yeah, we all did this in elementary school probably, or if you're not from America, maybe in a different currency. Okay, right, so this is not obviously a big deal. We're just adding up numbers. So that's all we're doing today. So subset sum will generalize that. So as input, I give you n numbers, x1, x2, up through xn. just integers, okay? And I also give you a target value. So I messed that up. So not only do I give you these n numbers, but I also give you a target value, which I call capital T. Okay, so I'm giving you n plus 1 numbers total. The n numbers are sort of like the coins, and the target is sort of like the 93 cents. So you want to find a subset of the xi. So the xi's, by the way, could repeat. There could be duplicates of numbers. That's fine. But I want to find a subset of the xi's. So maybe at most one x1 and at most one x2 and so forth. That sum to the target t. Okay. Or in the yes/no version of the problem, the decision version is, does there exist a subset that sums to t? Okay. All right, so here I have an example of 10 numbers, all between 1 and 20, and a target of 52. Okay, and the question is there a subset of these 10 numbers that add up to 52? Seventeen, 7, 10. Okay, 34, and then what? 11, 45, 18. That seems correct, doesn't it? Okay, good. Wow, that's not actually the one I had in mind. So I was very lazy. I just went to some website and I randomly generated numbers and I just chose all the even ones to add up to 52. But you guys found your own solution, so that's good. Okay, so there's actually at least two different ways, probably three because you can switch to 18s, or four because for both of them you can switch to 18s. But anyway, there's multiple ways then to add up to 52. All right, so this probably didn't seem that tough. Okay, but you had to stare at it a little bit, right? And like try to remember how to add up numbers with more than one digit at a time and all that fun stuff. Okay, so this is another example of a search problem in the kind of more abstract sense of the word, in the sense that you're looking for something that sums to 52, a subset that sums for 52. But in particular, you can recognize it when you find it, right? So given a subset, I can easily check to see that it adds to 52 and that you're only using at most one of each of the input numbers. So it's very easy to verify a correct solution. So in that sense, it's a search problem, like all the SAT stuff we had done previously. Okay, and all right, here's the usual poll. Will this problem turn out to have a polynomial time algorithm? Will it turn out to be as tough as SAT? Or will you not vote? Okay, so as usual, who's not going to vote? I don't believe you, but okay, apparently none. All right, so the remaining choices are, you think there will be a polynomial time algorithm, or you suspect it might be tough. Okay, who thinks it will come up with an algorithm? Okay, I think that's a clear majority. I'd say like 70%. And who thinks it's going to turn out to be tough? Wow, it's possible that everyone voted. Okay, good job, team. Those who aren't voting maybe stopped attending, so that's okay. All right. Okay. Okay. Good. So, all right. I'll just ask, for those who voted for an algorithm, what was your intuition? What were some of your thought process? It could be just for fun, whatever you want. I'm just curious. Why did most of you think there'd be an algorithm? Sorry? Lead code. Okay. So somewhere on the internet, you've seen an algorithm for subset sum. Okay. Or maybe some interview practice or something. Okay. Those who thought it might turn out to be just as hard as, Boolean SAT, why did you suspect that? Was it bad vibes again? Oh, yes. Okay. One vote for bad vibes. Any other Yeah. Okay, so this is sort of an interesting feature. Um, if the answer was no, right? Suppose there was no subset sum. It's hard to think of a clean way to prove it. If the answer is yes, you can prove it's yes by providing the subset. But the answer is no, it's not clear how to convince me the answer is no, right? And that actually is uh, a reasonable heuristic, right? When you're looking at a new problem, you can ask yourself, not only it, does a yes answer have a nice kind of certificate or proof for it, but another question you can ask is, would a no answer have a nice certificate or proof for it? Okay, so that's a reasonable thought process. So a lot of easy problems, it is actually obvious how you would demonstrate no as well. Okay, interesting. Okay, good. There's fancy names for it, but I'll bring that up later in the class. Okay, so we're going to try to take the lead code approach first. Okay, so if I wanted to do an algorithm for subset sum, what are some ideas? Just high level ideas or buzzwords or anything. Yeah. Okay, so maybe something like digit by digit style thing. So if T has like a bunch of digits, um, then at some level I need to do something that addresses this slot. Those numbers have to add up, and those are only one digit numbers. And then, well, it's a little bit ambiguous what happens when you start carrying ones, right? Because you have some options, right? In order to satisfy the last digit, you can do it while carrying one, or two, you can carry two or carry three. You might carry more, might carry less. But maybe that could be addressed somehow in an algorithm, still working from the smallest digit on up. Okay, that's an idea. I actually hadn't thought of that. Any other ideas? Oh, we can try to do some kind of recursive algorithm. Okay, so let's try that because that's what I've got set up on the next slide. Oh, that should not be there. Okay, so if I wanted to, oh, that came out terribly. Okay, that's better. Okay, if I wanted to make a recursive algorithm, we'll first set up some kind of sentence that we can implement. All right, so who wants to contribute a sentence? Yeah. Okay. Sure. So I'll write SS to stand for subset sum. So okay, just what should the inputs look like? Okay, so maybe some subset of numbers. Okay, so I have some n numbers, or it could be less, right? But I take as input a set of numbers, and okay, and let's say I want to do the yes/no version, just to answer yes if there is a sum, no if there isn't. If there is a subset sum, and no if there is. All right, so this one's a pretty straightforward one. It's more or less stating the original question. We'll just say it'll answer yes if a subset of the xi's sums to t and no otherwise. Okay. I mean, I always just start with the simplest sentence that roughly restates the question, and then maybe later I might find out that, oh, it's not strong enough. I have to add some flags, some bells and whistles, or something like that. But I usually start here and see how far it gets me. All right, so, okay, that's the same sentence. All right, so if I want to implement this, right. How would I implement this? Sorry. All right, give me some base cases. Okay. Okay. Any other base cases? If n is equal to 0, return false. At this point, t is not equal to 0, because if t was 0, we already exit. So if n is 0, return false. Okay. Any other base cases, or if you want to proceed to the inductive case step? Huh? Well, sure. If n is equal to 1, then yeah, you might not. You might not. We can see afterwards. All right, if there's no other base cases, we can, or if you guys have more base cases, let me know. Otherwise, we can also do the next step. So at this stage, n is at least 1, t is not 0. Okay, yeah, so one thing, by the way, is that I am assuming that all the x's are positive integers. Okay, so you won't be subtracting anywhere. I could have defined it otherwise, but for positive integers, this is fine. So, okay, if t is less than xi for all I, then return false. Okay, fine. It's sort of like another base case. Okay, yeah, if t is greater than the sum. I feel like you guys are avoiding the actual real step. Then false. Okay. At some point, we're gonna have to really take a leap of faith here. Yeah. Okay, so now we're gonna, if there is a solution that either includes x1 or not, and we don't know which, right? So I can have one recursive call for including x1 and one recursive call for not including x1. All right, so in other words, I'm gonna have like 2 calls to subset sum, and I'll return like the or. If any of them comes out true, then the answer is true. All right, so we'll start out with the one where I do include x1. What does the subproblem look like? All right, x2 to xn. And then now I'm going to subtract x1 from t because I've already forced it in my solution. And then what would it look like if I didn't include x1? Okay. If you don't include it, then t will stay the same. Okay. All right. These lines will actually potentially make your code slower because you're introducing a loop over all the elements, so I'm just going to get rid of it for you. Okay. All right. So I think that's what I had. When I write it ahead of time, my handwriting is much better. I rewrite and rewrite and rewrite, so I don't look like a child. Okay. All right. So if we just had it like this, right, and if this was the algorithm, what would the running time be? Or how would we model the running time recursively? What would T of n be? Okay, so 2 subproblems of one size smaller, right? So you have your tree would look like this. It's gonna be a binary tree, but the problem is it's going to be very deep, right? So how many levels will this tree have? And so down at the bottom, how many leaves will we have? 2 to the n. Okay, so this is an exponential running algorithm. All right, but how can I make this algorithm faster? Caching. Okay. All right, so all I've done here is in the sentence, I just wrote it a little differently just so it's easier to imagine it being in a table. So instead of, now like x1 to xn is fixed globally. And when I use the parameter I, that means I'm using the numbers I through xi through xn. Okay, so SSIS means I'm trying to figure out a subset of xi through xn that sums to s. Okay, so this way my table just has an index for I as opposed to an index for all the weird subsets. Okay, otherwise this is the exact same code as before. I added, I think, one more base case compared to you guys, which is that if s is less than 0, I immediately return false because all the numbers are positive. Okay, otherwise it's the same code. All right. Okay, so how many subproblems are there, excluding the base cases? N times t subproblems. And how much time does it take per subproblem? 1. So how long does it take overall? Nt. All right, good. All right, so simple dynamic program. I think this is actually much simpler than some of the examples we did earlier on, or on the test. Okay, all right, so in light of this algorithm, previously, let's see, what was our vote again? We had, all right, 30% of you thought it was going to be hard, 70% was going to be easy. All right, so before it was 70-30, and I want to see if anyone's going to change their mind. So first of all, does anyone want to abstain the second time around? No? Okay. All right, so in light of the fact that we have an n times t algorithm, who wants to now maybe convert to polynomial time? Who thinks there's a polynomial time algorithm? Does the question make sense? Okay, so before we had 70% saying that we'd have a polynomial time algorithm and 30% who said no. And we just gave this algorithm, was this running time. Okay, so I just want to see if any of the 30% would change their mind. So who now thinks we would have a polynomial time algorithm? Okay, and who thinks this is going to turn out to be hard? Okay, somehow this number has gone up after our algorithm. I don't, okay. All right, why did more of you now think it might be tough? Or how come not everyone raised their hand to say we had an algorithm? Besides bad vibes, yeah. Ah, perfect, okay. All right, so you guys have seen this a couple times by now. So t only takes log t bits to write down, okay? So if t was small, which is maybe if you're actually making change for $1, t is 100 or something, it's not that big a deal. But in general, t can be big. What if t was something close to 2 to the n? It only takes n bits to write that down, right? So it doesn't actually increase the overall input size. But your running time is now n times 2 to the n. Okay, so we actually don't have a polynomial time algorithm as it stands. Okay. All right. Any ideas for improving then? So I think we did the most natural approach. We first tried something recursive, then we added caching. NT probably looked pretty good for a moment. Okay. All right, then we're going to try to do the other side. All right, so let's try to ask then the opposite question. Can we instead show a subset sum is hard? as hard as SAT. Now, compared to previous discussions, subset sum doesn't look anything like SAT, right? Maybe it's more believable that 3 SAT is as hard as SAT because at least the word SAT is in the name, right? And same with max 2 SAT and stuff like that, right? So that was maybe more palatable, easy to digest. Doesn't quite explain why 2 SAT turned out to be easier, but still, at least there's something Boolean-ish going on. Here we have numbers. We're just adding up numbers, right? We never thought that was going to be very tough. Okay, so, all right, so that's sort of the weird thing that's going on. Can we make a comparison now between subset sum and a problem that looks nothing like subset sum? Yeah. Mm-hmm. Sorry?
What we are doing now is to look at each number and to decide if each number belongs to the total. So is it,
Mm-hmm.
okay, is it similar, can we say it's similar to SAT or Boolean conjunction?
Yeah, that's basically, yeah, I think you're roughly restating the question. Okay, so again, the problem is pretty simple, right? The input consists of n numbers and a target, and you want to see if some subset of the n numbers can add up to t. And we kind of came up with an okay algorithm, but not actually polynomial time. It might be practical if t is small in many situations, but as far as this kind of basic question, fundamental question of a polynomial time algorithm, it doesn't count. So yeah, is this similar? You had a suggestion or question?
Yeah, I was thinking that we do have circuits for addition. So perhaps we could take the numbers and build circuits for whether you add the number or not, and then do a circuit SAT problem.
Okay, so okay. I think I understand your point. So I think what you're showing, so would this demonstrate that circuit SAT can be used to solve subset sum? Okay. So yeah, so given an instance of subset sum, I do think I can write a circuit. I mean, I can write a program that roughly checks to see, yeah. So I can write a circuit that maybe is satisfiable if and only if you come up with numbers that add up to S, right? Or maybe I can take this, because this addition problem is roughly a logical problem, right? And we even had SAT formulas for addition. I had some big long formula, if you remember. So maybe you can imagine trying to write a Boolean formula that takes as input n bits, 1 or 0, right? And true means I include x1, and false means I don't include x1. And for the second variable, it will be the same way. And that formula will come out to be true if and only if the sum, the numbers corresponding to the true Booleans add up to t, right? So that shows, or that would show if we pulled it off. Surely it would be messy, but I believe it's doable. That would show that SAT can be used to solve subset sum, or circuit SAT can be used to solve subset sum, and we know SAT can solve circuit SAT as well. Okay, so I guess the hard direction is whether subset sum can be used to solve SAT. In other words, you're given like a completely general Boolean equation, right? That's encoding who knows what, and you want to turn it into an addition problem where the Boolean formula can be satisfied if and only if the numbers add up to t, or some subset of numbers adds up to t, right? But that seems like a stretch, right? That seems tough. Okay, but nonetheless, that's what we're going to try to prove. Okay, so we're going to try to show that a polynomial time algorithm for subset sum implies a polynomial time algorithm for SAT. Okay, so what does that mean? So so what the high-level design should look like is, you should be taking as input some kind of SAT instance. So I'll choose 3 SAT because it's just easier to know there's only 3 variables per clause. We already know 3 SAT is as hard as SAT or as hard as circuit SAT. Okay. And somehow we need to take that and produce a set of integers and some target number. Right? So you're going to take a formula, you're going to spit out a bunch of numbers, right? And you should be able to feed that into a black box that solves subset sum, right? It just takes your integers and answers yes or no, okay? And then somehow we need to take that yes or no for a subset sum and interpret as a yes or no for the original problem, right? So if we're actually going to prove this thing, this is the approach we need to take, or at least this would be a sufficient approach, right? But it's a very weird approach because it's not at all true or clear how I can take a formula and make it turn into numbers, or how numbers can somehow express. Like numbers don't seem as expressive as Boolean logic, right? Like at some level, computers decompose to Boolean logic. So Boolean logic can do a lot of stuff: if, else statements, assignments, all these things. Numbers, you're just adding, right? They seem kind of crude compared to Boolean logic. It's not clear how 1 + 2 + 3 has anything to do with if, else statements and assignment and all the richness that comes with Boolean algebra. Okay. Does anyone want to speculate about some ideas? As usual, this is your one chance to guess, because once I show you the answer, you'll never guess again. Yeah. How can I get like really somehow numbers that describe logic? Okay, so for every okay, so just help me out a little bit. So you have a bunch of clauses, right, that have 3 variables each. So for each clause, you want to generate a 1 or a 0. Well, we don't know if the clause is true or false until we set the values for x. Okay, so one sec. So are you suggesting that, I take as input m clauses and I'm going to output m integers? Okay, so I have some clause x1 or x2 or not x3, right? What would and remember, there's no values to the x's because we're just describing the formula. So x is not like particularly assigned to true or false. What number does this translate to? You said 1 or 0 depending on whether it's true or false, but we don't have any xi values. Yeah. Okay, so maybe somehow the C1th bit should be corresponding to the, I don't know. In other words, can we play some games? So I think, okay, can we do maybe 1 bit per clause? Is that maybe an idea? Okay, so I think one suggestion then, and this is almost implicit in the fact that we already know we have an algorithm if all the numbers, if t is really small. So if this problem is going to be too hard, we might need large numbers. And one way to generate large numbers, if we sort of had like 1 bit per clause, right? So more generally, I think what you guys are gradually converging to is this. Numbers in a computer are also bit strings, right? So I have all these bits I can play with, and I can kind of almost treat separately from one another. And so I can try to use many digits, and maybe each digit can encode a different constraint. Okay, so the high level idea, if I get a bunch of subsets to add up to the target, right, then every bit needs to match. Every bit needs to match. If somehow like matching a bit corresponds to satisfying some piece of logic in that 3-sat, some logical rule, so to speak, then satisfying all the bits is like following all the rules. I'm only speaking very abstractly. I'll unveil some details in a second. But that's sort of, a high level trick is that numbers still have a lot of bits at their disposal. And, they're numbers, but we can kind of treat them as like bit strings, encoding a lot of information, packing in information into these numbers. So how are we going to do that? So as a preliminary step, just to get us from 3-sat to subset sum, I want to first recast 3-sat as a problem that looks a little bit more like taking a subset. This part's a little artificial. It has not much to do with numbers yet. So what I mean is this. So we have 3-sat, right? So it has a bunch of clauses, m clauses, and n variables. And to make it look like a subset problem, I can think of, letting capital X denote the family of all the literals. X1, not X1. X2, not X2. And I can think of each clause as some set of 3 literals. So, and again, this is just a superficial thing, so it looks more like subset before worrying about the sum part. Okay, so in this kind of terminology, my goal is to choose a subset of the terminals, some set S subset X, that satisfies 2 rules. All right, what are those rules? So I'm trying to translate 3-sat to can you find a subset of X that satisfies something? What should it satisfy? Sorry? So X is a set of all literals, right? And so S should map to a satisfying assignment, right? So my goal is to take 3-sat, where the goal is to find a satisfying assignment, and recast it or reinterpret it as some kind of subset problem. Try to find a subset of literals that satisfies certain constraints and rules. So what would those rules be in this terminology? It's an awkward question. Does the question make sense? Yeah. Yeah, so one of the rules is I can only choose X1 or not X1. I can't be choosing both, right? Because I can only be assigning something to be true or false. Okay, so that's, I think that's rule B. All right, so for each variable xj, S, our set S needs to contain exactly one of the 2 literals corresponding to it. Okay, and what would be the other rule? We need something for the clauses. Yeah, so how would I encode should not be false, but in the terminology of sets, in terms of S as a set problem? Yeah. Yeah, so for each clause CI, where I think of CI as a set of 3 literals, CI intersected with S should not be empty. Should not be empty. A clause. So some clause CI, which is, maybe like X1 or X2 bar. From the original formula. Okay. Oh, okay, so I need B because I'm not allowed to set xj to be true and false, right? I either set xj to be true or I set xj to be false. So in terms of our set thing, so we're trying to find a set of literals where choosing xj is like setting xj to be true, and choosing xj bar is like setting xj to be false. And I want to make sure that I satisfy all the clauses, which in our set terminology is like saying for each clause, ci, which has three literals in it, my set S needs to contain at least one of them, right? So taking x1 is like setting x1 to be true. And I'm not allowed to set x1 to be true and false, so that's why we have rule B, saying I can only take x1 or x1 bar. Yeah, I'm just trying to change the terminology a little bit so that the terminology is a little bit closer to what we see in subset sum. Right? I'm just trying to think of it as a choosing some subset of stuff to satisfy something instead of setting stuff to be true or false to satisfy a formula.
For the requirement A, is the one of the elements in CI is included in S, it's still true.
That's like saying we satisfy CI because we took if CI had like x2 bar and we have x2 bar, then that means we are setting x2 to be false, so we will satisfy CI. Yeah. Okay, so this wasn't supposed to be the hard part. The hard part's coming up. This was just some translation. But it's good to make sure we're on the same page here, since it'll get more complex in a moment. So any questions? Okay. All right. Okay. All right, I have it on the right. All right, now here's the part where we actually start making numbers. Okay, so now we're actually going to turn it into a subset sum problem. And we're actually going to have m plus n digits, where n is the number of variables and m is the number of clauses. So these will be very big numbers. And we're actually going to do base 4. So instead of doing bits, it can be 0, 1, 2, or 3, which of course you can turn into a bit string afterwards, right? It's not hard to convert from base 4 to base 2. Okay, so but base 4 makes it a little bit easier. All right, so what we're going to do is we're going to create, so, in the set problem, we're choosing a subset of literals, right? And subset sum, we're choosing a subset of numbers. So what we're going to do then is we're going to have for every literal a number. So for every xi, we'll have a number, and every xi bar will have a number. So for the literal xj, okay, we have m plus n slots, where the first m slots will be for the clauses. First slot is for the first clause, second slot is for the second clause, and so forth. And then n slots, one for each variable. Okay, and then here are going to be the rules. All right, so for each clause ci, if the literal xj appears in the ith clause, I'll set that digit to be 1. And if not, I'll set that digit to be 0. So like maybe xj is in the first clause, but it's not in the second clause, right? And you have various zeros and ones. Okay, so this is just indicating which clause is in and which clause it's not in. Okay, and then for the other one, we have one slot for every variable, and for the literal xj, I'm going to go to the j slot and set that to be 1, and I'm going to set everything else to be 0. Okay, so it's only a 1 in the slot corresponding to that variable and 0 everywhere else. Okay, so somehow we have this big, long base 4 string, but it's all ones and zeros. Okay. And we're going to do xj bar in the exact same way. So I highlighted the differences. Okay. So instead of calling it aj, I'll call it aj bar. Okay, so xj will get mapped to the number aj, xj bar will get mapped to number aj bar. And again, I'm only going to put a 1 in the slots where xj bar appears. I'm going to, the clauses, and I'll put a 0 for the clauses that it doesn't appear. And then I'll put a 1 for the xjth variable. Okay. So same idea as before. I just introduced some bars. Okay. Yeah, so there's only n slots here for the n variables. So xj and xj bar will both have a 1 in the same slot. Yeah, which is the one corresponding to the jth variable. I know it's a little confusing because xj refers to both the literal xj and the variable xj. Yeah, so aj and aj bar will have the same 1 in the variable section, and the same zeros over there, but the clauses will generally be completely different. Okay, so I'm kind of creating these bit strings that's encoding which variable this number comes from. Is it coming from xj or xj plus 1, right? And it's also encoding which clauses the literal corresponding to number participates in. Right? So roughly all the information from the problem is encoded in these numbers. Okay? And it's still polynomial size. It's m plus n bits might look like a lot, but it's a polynomial, right? So it's not blowing up that much. All right. Okay, so let me do a correspondence between that sort of set version of 3sat that we went through and our sort of new version. Okay, so those literals, x1, x1 bar, all the way through, they're now mapping to a bunch of these long numbers, a1 and a1 bar up through an and an bar, as constructed. I put it on the bottom right, not that it's easy to read. Okay, so a set, a subset of literals, S subset of X, is going to how would I interpret it in like numerical terminology? If that makes sense. So I'm kind of trying to do some kind of mapping between one problem and another. And they kind of speak a slightly different language. So a subset S of literals would correspond to, sorry? Oh, or maybe this is just too awkward of a question. So to a sum. Okay, so I want to think of a subset on one hand as corresponding to the sum of those numbers on the other. Okay, so I'm summing up all the AJs and AJ bars where the corresponding literal appears in S. I just define D to represent the sum. D is equal to the sum. So if you look in you see how I'm only summing over xj and S and xj bar and S? Okay, so D is just what I'm calling the sum. It's a new thing. Okay, yeah, so just a name. Okay. All right, so now what I want to do is, so we had these two rules, right, in the set version of 3sat. So one rule was that for every constraint I, it needs to have some non-empty overlap with S. And the other rule was that for every variable J, S should only contain exactly one of those literals, right? So now what I want to do is I want to try to interpret that in terms of D. Okay, so how would I interpret, in terms of D, how would I interpret this rule that Ci and S is non-empty? Yeah, okay, perfect. So those those bits corresponding to CI, in particular, if I'm just doing one CI at a time, that bit should be at least 1, right? Because that corresponds to taking taking at least one literal for that clause. Okay. All right. And then what would be the corresponding kind of rule for D for the constraint saying that I can only have one literal for each variable? Yeah. Sorry, the question is why 1? Well, I wrote at least 1. Okay, so just to maybe backtrack then, if I'm looking at, maybe this is the slot corresponding to the first constraint C1, right? So it's going to be 1 if the literal is in it and 0 if not. So in order to get this digit to be at least 1, I have to take at least one of the 3 literals that are in C1. So it's 3 sat, right? So whatever clause C1 is has 3 literals in it. And the only numbers that have a 1 in that digit are the numbers corresponding to the literals in that first clause. So the only way for me to get that first digit of D to be 1 is to take at least one of those 3 numbers. Okay. So yeah, so I think it has nothing to do with the XJ bar if we're on the same page. And this construction is a little bit complex, so maybe when we see it all together, in hindsight, it all fits. Okay, so now we have, okay, so that resolves, or that partly resolves stuff to do with constraints. How do I translate the rule for the variables, right? For each variable, I'm only allowed to take one of the 2 literals. Yeah. Okay, good. All right, so for all the variables xj, the corresponding digit should be exactly 1, right? That's saying I took one of the 2 numbers for that literal. Maybe that answers your question partially. Okay, so, all right, so I started with 3 sat, and now I have kind of a numerical question. Find a subset of numbers that, adds up to some D, so that D, for each of the constraints, that digit is at least 1, and for all the variables, that digit is 1. Okay, so I've kind of encoded 3 sat now to something that looks a little bit more numerical. Okay, this is not quite a subset sum problem though. What's missing, or what's off? Okay, we need a target value t. Okay, and so, yeah, what should t look like? What would t be? I guess you have a bunch of slots for the clauses and you have a bunch of slots for the variables. What would the clauses look like and what would the variables look like? Okay, so the clauses should be 1, 2, or 3, which is a little bit weird. The variables should all be 1, right? But the problem is that this thing here, right, is I have this greater than equal to 1 instead of equal to something. Okay, so what I want to do next is try to figure out, in other words, we're very close to finishing, but there's one bug in our construction. And that is that our kind of constraints for the clauses is expressed with a greater than equal to instead of an equal, right? So I can't come up with a good t because it could be 1, 2, or 3 for that digit. Okay. All right. That's the only bug we have left, and you guys might be able to fix it from here. All right. how might I try to rectify this detail? We're very close to done. As a hint, we have a lot of degrees of freedom. For example, we can make new numbers, right? You're allowed to do that. You can change the construction a lot of different ways. Yeah,
For each of the m digits that represents a clause, you can make a number that's just one of that digit and have two copies of each.
perfect. Okay, great. So we know that 1, 2, or 3 is okay, right? So anything between 1 and 3 should be okay. So if I set it like equal to 3, and I made it easy to go from 1 to 3 or from 2 to 3, then this way, like if you have some number that's like 1, then maybe I can just pad it and get it up to 3, right? But 0 should not be allowed to get up to 3. That makes sense, right? So that means you should be allowed to add 1 or 2 to that slot for free, but you can't add 3 because that would give you too much. So that's exactly what we're going to do. We'll just like give some free padding for each of those digits corresponding to clauses. Okay, so for the CI digit, I'll introduce 2 copies of what I'm calling BI. Okay, so BI just has a 1 in the digit corresponding to that clause, and a 0 everywhere else. And there's 2 copies. So this way you can raise a 1 to a 3 or a 2 to a 3, but a 0 can't get all the way up to 3. 0 can only get up to 2 if you have 2 copies. Okay, so we'll introduce 2 of these copies for every constraint, and that little buffer will let you basically say that 1, 2, or 3 is okay, because they can all be fixed into a 3. Okay, good. So that's what we'll do then, is now we have the original AIs from before, plus we have 2 copies of BI for each of the clauses, B1 through BM. Okay. And all right, what should T be now? What do I want to set the target to be? Yeah, 3s and 1s. So 3 is for all the clauses, 1's for all the variables. Okay. And now if you have some subset of the AIs and AI bars and BJs that sum to, say, D, right? We know that for a clause, that digit will be 3 if and only if you have at least one of the literals, AJ and AJ bar, AJ or AJ bar, right? And we know that for each variable, that corresponding digit is 1 if and only if you have exactly one of AJ or AJ bar for that variable xj. Okay, so we're just kind of encoding one constraint in every digit. Okay, good. So that is ultimately the entire construction, right? So we start with 3sat, and we create the subset sum problem. We're using tons of digits to encode all the little rules, so to speak, for 3sat. The rules are you can only set xj to be true or false, and you have to set, get at least one literal for every clause. We plug that into our black box, and yes or no for the black box will also tell us yes or no for the original 3-sat formula. Okay, makes sense? Any questions? Great. So we're actually done early. If you want, I can set up one of the homework problems, or we can just go home. We'll call it a day? We'll call it a day. All right. And I'll just answer questions ad infinitum up here. All right. Thanks, guys.